So we'll control the synchronous motor now from a cycle converter. It is a self-controlled synchronous motor fed from a cycle converter. Okay, so the circuit diagram of cycle converter here. Okay, so now you see. So okay. Okay, now we'll do the connections. Okay. Okay, these are the connections. So you'll have similar connections for the other two phases also. So second phase. Now third phase is also similar kind of connections are there. Okay, now we'll see here. First, we'll see here that you have the cycloconverter here. You have a cycloconverter here. So let me take the synchronous motor now. Okay, so this is your stator. This is your rotor. So you have all the three connections through the cycloconverter. Through the cycloconverter. Okay, then here we have this. Here we have this. Okay, this is the connection. Whereas the rotor, okay, you have the field winding to the rotor. Okay, then I hope you know this thing that there is a speed sensor here. There is speed sensor here. Then from here it will go to the control circuit. Okay, so yeah, what you need to understand here is, see, both the diagrams are same. Both the diagrams which I have drawn, they are same, except you have except this is a power circuit, whereas this is just a block diagram. The first one is the block diagram. So you see the block diagram here. This is your synchronous motor. This is your synchronous motor. So you are giving three-phase AC to the cycloconverter. So now I hope you know what is the purpose of this cycloconverter. It converts one frequency to the another frequency. So variable frequency supply will go to the stator of the synchronous motor. So I hope you know this thing that you can control the speed of the synchronous motor using this. Then you sense the speed. So it's a self-control. So self-control in the sense, you take the feedback definitely, and every time you monitor this speed here. Every time you monitor. So it's a rotor position sensor. So using this, you can sense the speed. Then based upon the error, that part is not shown here. Based on the error, the controller will take action, and the controller will definitely sense this, and based upon that it generates the firing angle pulses to the thyristors in the cycloconverter. So this is just a path. This is just a feedback path. Okay, this is how it does. Okay, see here, all these controls, what you have seen is that you see yourself that all these things, you sense this speed, and then you already, there is a set speed will be there. Then you have some error, or you may not have error. If you have error, then as per the error, it takes an action. So then as for the action, you get the, here you get the firing pulses. Okay, so I will say some alpha. So some firing angle, it will be decided based upon the firing angle. Okay, you will have the frequency here changing will be there. Okay, and this is how it works. Now the same circuit I have shown here. I hope you know this is a cycloconverter for single phase, for one phase for the, okay, that is for this case. Okay, so the power circuit. So you take the switching here based on the switching here. So I hope you know, you remember this operation of the cycloconverter. Then there is no point in discussing about this operation of the cycloconverter here. Some set of thyrisors will turn on at one time, some other set will turn on some other time. Okay, so based on that, so through the cycloconverter you are giving the, so the same block diagram. The cycloconverter here is that block is this one. Is block. Okay. Then after that, you have this stator, then rotor, then you sense the speed, then it goes back once again. Then after that, you go to the firing angle alpha. So, so now what kind of commutations you will find out in the cycloconverter we have discussed already somewhere. Okay. So step down cycloconverter, you have one type of commutation. Step up cycloconverter, it is natural commutation. It is forced commutation. Now, see the commutation you have heard this thing also. Line commutation, load commutation. What is meant by line commutation is that the turning off of the thyristor will occur as per the supply. As per supply. So supply will have negative voltage, supply will have zero voltage. So based on that, the commutation will happen. That is turning off will happen whenever there is a negative voltage from the supply side. Whereas load commutation in the sense, see, the load current will be there. Somewhere the load current will be zero. See the supply side zero crossing and the load side zero crossing may not be same because it depends upon the loads. If you have RL load, then the zero crossing will be extended further. If you have R load, then zero crossing of the current and the zero crossing of the voltage, both will be same. Okay, so it depends upon the load. So the some circuits you will have the load commutation, some other circuits you will have the line commutation. So this load commutation depends upon the load type of load. Okay, so load type. So just main difference I will tell you, the line commutation in the sense the turning off of the thyristors will occur, okay, when the supply is there. So supply side there is zero crossing will be there. So based upon that only it will be turned off. Whereas load commutation in the sense, the main thing I will tell you, load commutation in the sense it happens based upon the load requirement. Okay, you turn on thyristors, you turn off thyristors. Okay, so then the load current will cross somewhere zero. So the load will force some. You can say like this: the load will force the thyristors to turn off. That's a load commutation. And the line commutation in the sense the source will force the thyristors to turn off. That's the source. That's the line commutation. Okay.